Welcome back. In this module, we discuss about quantum computing and the long-term security of encrypted data. When encryption is discussed, it is usually framed in the present tense. How data is protected today, how systems are secured now, how attackers operate with current capabilities. Quantum computing forces a different perspective. It asks a longer term question. What happens to encrypted data when the assumptions underlying modern cryptography no longer hold? This section introduces quantum computing not as an imminent catastrophe, but as a strategic risk that reshapes how we think about data protection over time, particularly for information that must remain confidential for many years. Why quantum computing matters to cybersecurity? Quantum computing is often portrayed as science fiction or distant speculation. In reality, it represents a fundamentally different way of performing computation. Traditional computers process information in bits that exist as either 0 or 1. Quantum computers use quantum bits or qubits, which can exist in multiple states simultaneously and exhibit properties that allow certain calculations to be performed far more efficiently. Most computing tasks do not benefit dramatically from this model. Cryptography does. Certain cryptographic problems that are effectively impossible for classical computers become tractable, at least in theory, not sufficiently powerful quantum systems. This is why quantum computing is a cybersecurity concern even before practical machines exist at scale. Public key cryptography and its assumptions. Modern encryption relies heavily on public key cryptography. Asymmetric encryption, digital signatures, and secure key exchange all depend on mathematical problems that are easy to compute in one direction but extremely difficult to reverse without a secret key. Examples include factoring very large numbers, solving discrete logarithm problems. Classical computers struggle with these tasks when key sizes are large. The time required to break them is effectively prohibitive. Quantum algorithms change that assumption. What quantum computers threaten and what they do not. Quantum computing does not break all encryption equally. It primarily threatens public key cryptography, the systems used for secure key exchange, digital certificates, authentication, digital signatures. Symmetric encryption, when properly implemented with sufficiently long keys, is far more resistant. It may require longer keys, but its foundations remain viable even in a quantum context. This distinction matters. Quantum risk is not about encryption disappearing. It is about cryptographic assumptions remain safe and which do not. The harvest now, decrypt later problem. One of the most important quantum-related risks has nothing to do with present-day quantum computers. It is known as harvest now, decrypt later. Attackers can intercept and store encrypted data today, even if they cannot read it. That data may be decrypted in the future once quantum capabilities mature. This creates long-term exposure for information that must remain confidential over extended periods such as personal data, financial records, health information, intellectual property, or state secrets. Encryption that is strong today may not be strong tomorrow. Why this is a strategic risk and not an operational one. Quantum computing is not a near-term operational threat for most organizations. You're unlikely to experience a quantum breach tomorrow, but it is a strategic risk for data with long confidentiality lifespans. If information must remain protected for 10, 20, or 30 years, then future cryptographic breakage matters today. This is particularly relevant for regulated industries, long-term records, and systems that archive data rather than discard it. Post-quantum cryptography, adapting before the shift. The response to quantum risk is not to abandon encryption, it is to evolve it. Post-quantum cryptography refers to cryptographic algorithms designed to resist both classical and quantum attacks. These algorithms rely on mathematical problems that are believed to remain hard even for quantum computers. Standardization efforts are already underway. However, transitioning cryptographic systems is slow. Encryption is deeply embedded in protocols, infrastructure, hardware, and software. Change takes time, often measured in decades. This is why quantum preparedness must begin long before quantum capability becomes practical. Why crypto agility matters. Crypto agility refers to the ability to change cryptographic algorithms without redesigning entire systems. Systems that are rigidly tied to specific encryption methods will struggle to adapt. Systems designed with flexibility can evolve as standards change. From a governance perspective, crypto agility is a resilient strategy. It acknowledges that cryptographic assumptions are not permanent and plans accordingly. Data retention as a quantum risk factor. Quantum risk is magnified by poor data retention practices. Data that is kept indefinitely increases exposure. Information that no longer serves a purpose but remains stored creates future liability. This links cryptography to privacy and data governance. Minimizing unnecessary data retention reduces the impact of future cryptographic compromise. What cannot be decrypted cannot be exposed. Separating hype from reality. Quantum computing attracts exaggerated narratives, both optimistic and catastrophic. From a cybersecurity perspective, the truth is more measured. Quantum computing does not instantly break all encryption, it does not eliminate the need for security today, and it does not require immediate panic. But it does require foresight. Organizations that treat encryption as static risk being unprepared for inevitable change. Why this matters in the AI age? AI and quantum computing are often discussed together, but they introduce different types of risk. AI accelerates attacks in the present. Quantum computing threatens assumptions over the long term. Both challenge traditional security thinking. Understanding quantum risk reinforces a broader lesson. Cybersecurity is not about defending against one moment in time. It is about managing risk across time horizons. The governance dimension of quantum risk. Addressing quantum risk is not primarily a technical task. It involves understanding data life cycles, classifying information by sensitivity and longevity, planning cryptographic transitions, and coordinating across vendors and systems. This makes quantum preparedness a governance issue as much as an engineering one. The key takeaways are quantum computing does not break encryption today, but it challenges the assumption that today's encryption will remain safe forever. For data that must remain confidential over long periods, future decryption is a present day risk. Managing that risk requires foresight, crypto agility, and disciplined data governance, not fear or speculation. Encryption is not static, neither is security.